Okay, good morning students. In yesterday class, we discussed about expression for electric field due to a dipole on its axial line and also equatorial line. These two are very most important 5 marks questions in examination point of view. Next, so in this session we learn about expression for torque. Expression for torque. Acting on a dipole kept in a uniform electric field. Uniform electric field, like this. Expression for torque acting on a dipole kept in a uniform electric field. So, dear students, what is meant by uniform electric field? Before that, what is meant by electric field strength? Electric field strength at a point in the field is defined as a force acting on a unit positive charge kept at that point. Already we know. Similarly, uniform electric field. Uniform electric field Okay, uniform electric field. So what is meant by uniform electric field? A force acting on a unit positive charge kept at any point in the field is same. Force acting on a unit positive charge placed at any point in the field is same. That is, same quantity of force acting on a unit positive charge which is kept in any point, kept at any point. That is called uniform electric field. That means the field, electric field in which force acting on a unit positive charge kept at any point is same. Same quantity of force will be acting. On a unit positive charge placed at any point in the field. That field is nothing but uniform electric field. So, uniform electric field means same quantity of force acting on a unit positive charge placed at any point in the field. That is called uniform electric field. Simply, force is same force acting on a unit positive charge which is placed inside the field at any point, which is kept at any point. Okay. Suppose, for example, see, dear students, this is the representation of uniform electric field. This is the uniform electric field representation. So, arrow mark indicates direction of electric field. Okay. In this field, so let us consider 3 points. This is the point P. This is the point R. This is the point S. Okay. Suppose just 1 coulomb of charge placed at P. Some quantity of force acting on it. So whenever, dear student, already we know, whenever some quantity of positive charge placed inside the field, some quantity of force will be acting on it. Okay. Of course, let us consider 1 coulomb of charge placed at a point P inside the field. According to Coulomb's law, some quantity of force will be acting on it. Or by the definition of electric field strength, some quantity of force acting on it. That force is F is equal to, suppose, Q Newton. And also 1 coulomb of charge placed at R. Same 1 Newton force will be acting on it. And also another 1 coulomb of charge placed at C, same force will be acting on it, that is F is equal to 1 Newton. So 1 coulomb of charge placed at different points in the field, same quantity of force will be acting on it. Same quantity of force will be acting on it. That is called uniform electric field. The force acting on a unit positive charge which is kept inside the field is same. The force acting on unit positive charge which is kept inside the field at different points, same quantity of force will be acting. Same quantity of force will be acting. So that is nothing but uniform electric field. Similarly, non-uniform electric field. What is meant by non-uniform electric field? Like this, non-uniform electric field. What is meant by non-uniform electric field? Force acting on a unit positive charge which is kept at different points is different. That means a unit positive charge placed inside the non-uniform electric field, force will be different. Different force will be acting. Not same. So that is nothing but non-uniform electric field. Now non-uniform electric field means force acting on a unit positive charge is different wherever the unit positive charge kept at different points. So that is nothing but non-uniform electric field. Same force will be acting, uniform electric field. Different force acting on that charge which is kept at different points, that is non-uniform electric field. See representation of non-uniform electric field like this. This is the non-uniform electric field representation. Suppose let us consider 3 points. This is the point P, this is the point Q, of course this is the point S. Similarly, same 1 coulomb of charge placed at P. What is the force? Suppose for example 1 Newton force will be acting. 1 Newton. See, so in this case same 1 coulomb of charge placed at Q. See 0.5 Newton. 0.5 Newton force will be acting on 1 coulomb of charge which is kept at Q. And same 1 coulomb of charge placed at S. Quantity of force will be acting, that is Q Newton. So same quantity of force placed at different points, force will be different inside the field. That nothing but non-uniform electric field. Uniform electric field, non-uniform electric field. So uniform electric field means force acting on a unit positive charge is same which is placed at different points. That means same quantity of force will be acting. Non-uniform electric field means force acting on a unit positive charge is different which is placed at different points. That is non-uniform electric field. Okay students. Okay. Now we discuss expression for torque acting on a dipole kept in a uniform electric field. Okay. So let us consider a uniform electric field like this. Dear students, this is the uniform electric field representation. Uniform electric field. Okay. This is the uniform electric field. E with the electric field, arrow mark indicates direction of electric field. Arrow mark indicates direction of electric field. Okay. See, expression for torque acting on a dipole. Let us consider dipole placed inside the field. Let us consider a dipole like this. This is the dipole. What is meant by dipole? Two equal and opposite charges separated by a small distance. That is called dipole. Okay, this is the dipole. So, and theta, the dipole axis. This is an axial line like this. This is an axial line of the dipole. Theta will be the angle made by the axis of dipole with the field. With the field. So, that is the dipole. That is the theta. Sorry, theta. That is the theta. So, theta be the angle made by the axis of dipole with the direction of electric field. Okay. See, what is the direction of dipole movement? Like this, P, from negative to positive, like this, negative to positive. So, R theta be the angle between direction of dipole moment and electric field. Direction of electric field. That is nothing but theta. Okay. So, whenever the dipole kept inside the uniform electric field, some quantity of force will be acting because of this is the positive charge. Some quantity of charge placed inside the field. Some force will be acting by the definition of electric field strength. Okay. So, this is the positive charge. In case of positive charge, the direction of force is along the direction of field. See, this is the direction of force. F is equal to EQ force acting on plus Q charge. Similarly, negative charge also placed inside the field. See, the direction of force in case of negative charge placed inside the electric field, the direction of force is opposite to the field. F is equal to EQ. Because same forces, because these are equal quantity of charges, but opposite sign. Force also same in magnitude, opposite in direction. Then, two equal opposite forces acting on the dipole will be rotated. However, net force acting on the dipole will be zero. But dipole will be rotated because of two equal and opposite. This force acts along this way. This force acts along this way. Then dipole will be rotated. Moment of couple or torque will be generated. Okay. So, dear students, torque tau is equal to force into perpendicular distance. Already we know that in previous last year classes, torque, force into perpendicular distance. Okay. So, torque tau is equal to force. What is the force? F is equal to EQ into perpendicular distance. I want perpendicular distance. Dear students, so this is the distance between the two charges. So, I will take 2A. 2A is the distance between two charges. Okay. So, in this case, I want perpendicular distance. See, this is the perpendicular distance. So, C, A, B, C. BC is the perpendicular distance. So, I want BC. So, this is 90. Degree. Okay, this is the 90. So, from the triangle, right angle triangle, ABC, sin theta how much? Sin theta how much? So, this is the theta. Sin theta, opposite side like this. This is the opposite side. BC divided by hypotenuse. This is the hypotenuse like this. This is the hypotenuse. 90, opposite side. Hypotenuse, that is what value? AC. AC means 2A. That is 2A. So, BC is equal to 2A sin theta. 2A sin theta. So, substituting BC value in this equation, then we will get torque. See, torque tau is equal to force EQ into, what is the value of BC? What is the value of BC? 2a sin theta. 2a sin theta. Okay. Torque tau is equal to E into 2aq. 2aq into sin theta. Okay, students, 2aq into sin theta. Combine this. 2aq into sin theta. Okay. 2aq means dipole moment. That is the dipole moment. What is meant by dipole moment? The product of either of charge and separation between the two charges. Product of either of charge and separation between the two charges. So that is nothing but dipole moment. So tau is equal to, this is nothing but P. This is nothing but P. P E sin theta. Since P is equal to 2aq. P is equal to 2aq. See, dear students, this is the very most important equation. This is the expression for torque acting on a dipole kept in a uniform electric field. Uniform electric field. See, tau is equal to P sin theta in vector form like this. Vector tau is equal to vector P cross vector E. Vector P cross vector E. This is the vector form. Tau is equal to vector P cross vector E. To remove the cross, sign is there. So, torque is the vector quantity. Torque is a vector quantity. This is the magnitude. What is the direction? The direction of torque is governed by right hand screw. Right hand screw. Right hand screw. Okay. Tau is equal to P cross E. P cross E. Okay. So what is the SI unit of? Okay. This is the final equation. This is the final. So very most important one, 3 marks. Up to this. Very most important. Okay. Small bit, very most important bit. What is the SI unit of torque? What is the SI unit of torque? Tau is equal to, dear students, P into E. Okay, P into E. P means dipole moment. What is the SI unit of dipole moment? What is the SI unit of dipole moment? Coulomb meter into electric field. What is the SI unit of electric field? Newton per coulomb. Newton per coulomb. Coulomb get cancelled out. Then in SI system, torque, SI unit of torque is Newton meter. Newton meter. So this is the SI unit of torque. So okay, students, see, a dipole kept in a uniform electric field. Note, very most important point. Very most important point, students. Very most important. A dipole kept in a uniform electric field. Net force acting on the dipole is 0 and the torque will be acting on it. Torque will be acting on it. And that means uniform electric field, force will be 0, net force will be 0. Please remember it, net force will be 0. Torque is there, some value, P sin theta. Non-uniform electric field. So, dear students, a dipole is kept in uniform electric field. Net force acting on the dipole will be 0. Torque will be some value. That is tau is equal to P sin theta. A dipole kept in non-uniform electric field. Net force as well as torque not equal to 0. Some value. Torque also experienced on the dipole and also force also experienced on the dipole. In non-uniform electric field, force is there, F is equal to EQ. and torque also is there, that is P is there. Both are experienced. This is the very most important. Once again I will repeat, whenever a dipole is kept in a uniform electric field, net force will be 0, only torque will be experienced on the dipole. And the second one is, a dipole kept in non-uniform electric field, force as well as torque both are experienced on the dipole. Why? Because of non-uniform electric field, same quantity of force. Two charges placed inside the field, force will be different. Not same force, because there is a non-uniform electric field. See, a unit positive charge placed inside a non-uniform electric field, force will be different. That's why net force not equal to 0. Okay, students. So next, another important bit. For what angle torque will be maximum and minimum? See, torque tau is maximum. What position of dipole, torque is maximum, or what angle torque is maximum. Torque is maximum if theta is equal to 90 degree, because of tau is equal to P sin theta. Substituting theta equal 90 degree, tau is equal to P sin 90 degree, that is equal to P. This is the maximum value of torque. So in this position, the dipole is perpendicular to the electric field. So whenever the dipole is perpendicular to the electric field, the direction of dipole is perpendicular to the direction of electric field, maximum torque experienced on the dipole. See, so this is the electric field, like this. This is the electric field direction. This is the direction of dipole moment, minus Q plus Q. The direction of dipole moment like this, P, from negative to positive. So in this case, what is the angle between the direction of dipole moment and the field? 90 degree. So in this position, torque will be maximum. See, whenever the dipole is perpendicular to the direction of electric field, maximum torque experienced on it. Okay. Next, another one, important one. At what position of the dipole torque will be minimum? Torque is minimum or 0. For what angle? If theta is equal to 0 degree, tau is equal to P sin 0 degree, that is equal to 0. For what angle torque is minimum or 0? Theta equal to 0, torque will be 0, because sin 0, 0 into anything is 0. Tau is equal to 0. In this position, in this case, the direction of dipole moment or the direction of dipole is parallel to the electric field or anti-parallel to the electric field, whatever it, parallel to the electric field. See, this is the electric field direction. This is the dipole, minus Q plus Q. See, this is the dipole moment direction. The direction of dipole moment and electric field both are in same direction. Theta is equal to how much? 0 degree. So tau is equal to 0. That is, whenever the dipole is parallel to the direction of dipole moment is parallel to the direction of electric field, no torque experienced on the dipole. experienced on the dipole. So please remember it, students. Theta. What is the theta? What is meant by theta? Theta be the angle between the direction of dipole moment and direction of electric field. Direction of electric field. Okay. So in this position, torque will be minimum or zero. This is nothing but stable equilibrium of the dipole. This is the stable equilibrium. Stable equilibrium of the dipole. Stable equilibrium of the dipole. Stable equilibrium. In this position, dipole will be stable equilibrium. Similarly, torque is minimum or zero. Tau is equal to 0 if theta is equal to 180 degree. Theta is equal to 180 degree means the direction of dipole moment is opposite to the direction of electric field. See, dear students, this is the electric field direction. So this is the dipole moment direction minus Q plus Q. So like this, negative to positive, negative to positive. In this case, both are in opposite. Of course, no torque acting on it. P sin theta. In this case, what is the value of theta? 180 degree. Substituting 180. Sin 180 also 0. So ultimately, torque tau is equal to 0. This is nothing but unstable equilibrium. In this position, dipole will be unstable. This is the unstable position. Unstable equilibrium position. Equilibrium position. Okay, these are the very most important students. For what angle torque will be maximum? Theta is equal to 90 degree. In that case, the direction of dipole moment and the direction of electric field both are perpendicular to each other. For what angle torque will be 0 or minimum? So tau is equal to P sin theta. Theta is equal to 0 degree. For theta is equal to 0 degree, torque tau is equal to 0. This is the stable equilibrium of the dipole. So in this case, the direction of dipole moment and electric field both are in same direction. Okay. Suppose electric field and dipole moment both are in opposite direction. That is theta equal 180. That is the, of course, torque will be 0. That is the unstable equilibrium. Unstable equilibrium of the dipole. Okay, students. So torque, expression for torque acting on a dipole kept in a uniform electric field is the very most important 3 marks question. 3 marks question. Tau is equal to P sin theta. Okay. Next one. Electric field lines. Very most important, another one concept. Electric field lines. Electric field lines. Electric field lines are electric field lines of forces. Whatever it, both are same. Electric field lines. Electric field lines means it is a track or a path in which a unit positive charge moves or tends to move is called electric field lines. Electric field lines means it is a track. It is a track or path in which a unit positive charge moves or tends to move is called electric field line. Suppose, dear students, so this is the unit positive charge like this, moving from point A to point B. Point B. So like this is moving from point A to point B. So a track, backside a track, just imagination, a track will be formed. Suppose if the track is created whenever a unit positive charge is moving from one point to another point inside the field. inside the field. This track is nothing but electric field lines. Electric field line. So electric field lines are imaginary lines. Electric field lines are imaginary lines. There is no physical existence. There is no physical existence. So what is meant by electric field line? It is a track or path in which a unit positive charge moves or tends to move inside the field. So that is called electric field lines. Okay, students. So properties, the very most important electric properties, electric field lines properties. Properties of electric field lines. Properties. So very most important, first one. Electric field lines are imaginary lines. There is no physical existence. Electric field lines are imaginary lines. There is no physical existence. There is no physical existence. Next one. Electric field lines are straight lines. Electric field lines are straight lines. They do not form closed loops. These are the straight lines. They do not form closed loops. They do not form closed loops. Next, third one. In case of isolated positive charge, electric field line starts from positive charge and ends at infinity. See, suppose, dear student, this is the positive charge. In case of isolated positive charge, isolated means single. In case of isolated positive charge, electric field lines start from positive charge, ends at infinity. Like this. Already we know that, students. So, in case of positive charge, the direction of electric field radially outwards. Same. Radially outwards. Electric field line, in case of isolated positive charge, radially outwards. Okay. So, in case of isolated positive charge, the electric field line starts from positive charge, ends at infinity. Next, fourth one. In case of isolated negative charge, electric field line starts from infinity, ends at negative charge. Okay, like this. So diagrams also very most important for 1 mark purpose. Draw the neat diagram of electric field lines in case of isolated positive charge and isolated negative charge. Very most important 1 mark bits. Okay. In case of isolated negative charge, electric field line starts from infinity, ends at negative charge. Okay. Next. Fifth property, students. Electric field lines originate at positive charge, terminate at negative charge. Electric field lines originate at positive charge, terminate at negative charge. See, dear student, this is the positive charge, this is the negative charge. Originate at positive, terminate at negative, like this. This is also a neat diagram of electric field lines in case of unlike charges. Like this. Dear students, arrow mark very most important. Without arrow mark, there is no marks in examination point of view. Without arrow mark, there is no marks. Okay. is the very most important diagram. So, in case of electric field lines, in case of two unlike charges, positive and negative. Okay. Fifth bit, fifth point, fifth property. Electric field lines originate at positive, terminate at negative. Terminate at negative. Next one, sixth one. Sixth one. Electric field lines are never cross each other. Electric field lines are never cross each other. That means electric field lines never intersect. Very most important one. Electric field lines never intersect. Never intersect. That is, never cross each other. Very, very most important. Because of these are the straight lines, like railway tracks. Never cross each other. Never cross each other. Suppose two electric field lines are intersect, that is cross each other. Electric field having two directions. That is, charge flows in two ways. It is not possible. It is not possible. Electric field lines, electric field, the direction of electric field always single direction. So, electric field lines never intersect. Suppose, see dear students, so this is the one electric field line. Of course, Q1 charge can flow. Q1 charge will be flowing from in this region. Similarly, this is the Q2 charge flow. Q2 charge is moving, Q1 charge is moving. These two lines are crossed like this. This is the point of intersection. Point of intersection like P. Suppose two electric field lines are intersect. See, in this point, in this point of intersection, Q1 charge. Okay. So in this way, Q1 charge may be flowing also, or Q1 charge also flowing in this way. So the charge, the direction of charge in two ways. The flow of charge in two ways, it is possible. So Q1 charge moving this way or this way. It is possible to two ways, but it is not possible. Really, because of electric field, the direction of electric field only single way, not two ways. Similarly, the charge Q2 also flows in two ways. It is possible to two ways. Like this is Q2. The direction of charge like this, in this way also possible, in this way also Q2 also possible. Flow of charge Q2 also moving in this way or in this way. It is possible to two ways. But in reality, it is impossible. Reality, the direction of electric field or flow of charge in one way, not two ways. Not two ways. If suppose two field lines are intersect, it is possible to flow in two ways. That's why electric field lines are never intersect. Never intersect. So this is the very most important one. Electric field lines are never cross each other. So like two electric street wires, two wires, street wires, never cross each other. Same manner. Okay. Next one. Seventh one. Electric field lines always normal to the charged conductor. Electric field lines always normal to the charged conductor. See, let us consider conductor. Suppose this is a cylindrical conductor. So charges, already we know that charges always accumulates on its surfaces like this. Charges always accumulates on its surfaces. Okay. So in case of charged conductors, electric field lines are always normal or perpendicular like this. These are the field lines. These are the field lines, electric field lines. So in case of charged conductor, electric field lines always normal or perpendicular. Suppose if the field lines are parallel to the charged conductor, suppose this is the normal. So suppose this is the parallel to the charged conductor. Suppose electric field lines are parallel to the charged conductor, that means charge flow in that way. Charge flow in that way, that means a current passing through the conductor. But in static electricity, charges remain stationary. So it is not possible. It is not possible. So electric field lines always normal to the charged conductor. Electric field is always normal to the charged conductor. See, suppose field lines are parallel to the charged conductor, like this, parallel to the charged conductor. So direction of electric field line means charge moving in that way. That means charge can flow through the conductor. But in our static electricity, charges remain stationary. So charges always remains constant. So charges do not move in this chapter. So electric field lines always normal to the charged conductor. Always normal to the charged conductor. Next, eighth one. In case of curved lines, in case of curved regions, see, this is the curved region. In case of curved region, this is a small point on the curved region. In case of curved region, the direction of electric field means a tangent line drawn at the point of path indicates direction of electric field. See, this is the curved region. Suppose let us consider point P on the curved region. Okay. So in case of curved regions, a tangent line drawn at the point of path, indicates direction of electric field. Suppose this is the one point Q. What is the electric field direction? What is the direction of electric field line? What is the direction of electric field in this point? Like draw the tangent line like this. A tangent line drawn at the point of path indicates direction of electric field in case of curved lines. Okay. So these are the main properties of electric field lines. First one is electric field lines do not form closed loop. These are the imaginary lines. There is no physical existence. Next one, in case of isolated positive charges, electric field lines originate from positive charge, terminate at infinity. Similarly, in case of isolated negative charge, electric field lines originate from infinity, terminate at negative charge. See another one, in case of unlike charges, electric field lines originate at positive charge, terminate at negative charge. Another one, electric field lines never intersect. Why? Because of two electric field lines are intersect, the electric field having two directions. It is impossible. So electric field lines never intersect. Next one, electric field lines always normal to the charged conductor or perpendicular to the charged conductor. Okay. Next, the last one. In case of curved regions, a tangent line drawn at the point of path indicates direction of electric field. Fields. Okay, students. Thank you.